Okay. All right. Okay. All right. So today we're still doing Riemann sums, but we're going to look at a couple methods that we can try that will be slightly more accurate than what we were doing yesterday. We're still looking at estimates, so these are not going to be perfect. So the first thing that we're going to look at is looking at using a midpoint Riemann sum instead of using a trapezoidal Riemann sum. For the sake of time, I am going to cheat and use a Desmos graph right here. Even though we can't use Desmos. Yeah, in honor of Coach Wood, who's leaving us tomorrow. His last day tomorrow.
Do you think he'll be a substitute? They better play all
No, because he's going to be teaching at Galax High School, so he won't be back here because he'll be teaching up there. So, all right, let's get this. No, he's getting paid his retirement plus his salary for teaching up there. That is why he is doing this. He will be making a lot more money for probably, even though he has to drive an hour, probably less time because he's not coaching. Can't say I blame him, but I will miss him. Okay. Yes, tomorrow is his last day here. Thursday is his first day there. So. Yeah. Yeah, well, that position has been open for over a year. They can't find anybody to do it. And Virginia pays teachers better than North Carolina. Right now, their current math teachers are having to teach 4 math classes all day with no planning period. Which you guys don't realize how horrible that would be as a teacher.
Do they get paid more for doing that?
I think he said they do right now, but I imagine they'll be grateful that he's there so that they don't have to stay, because I would have to stay so late. I mean, I guess maybe if you don't, I don't know. All right. Okay, let's look at this graph right here. So for the sake of time and so that it looks pretty, I have put a Desmos graph up here. And we're looking from 0 to 4. And it tells us to use 4 rectangles, but this time we're going to use the midpoint Riemann sum instead of a left or right Riemann sum. So let's look at what that would look like here. So I'm going to split this into 4 different sections right here. And what I'm going to do for this, instead of putting the left corner or the right corner of my rectangle on the graph, I'm going to put the middle of the rectangle on the graph. So what that's going to look like here is, like right here is this point. This first one's going to be really hard to see. I would have this little teeny tiny rectangle right here. This one will be easier to see right here. I'll have this rectangle. This one right here, and then this one right here. You can kind of see this is going to give you a little bit better estimate because your rectangle is sort of splitting the 2 areas, and each rectangle has a little bit above and a little bit below the graph, right? Now, it does mean you can't really tell whether this is going to be an over or under estimate, right? We can't tell for sure which one it's going to be here very easily, but this is going to give us a little bit better estimate. So let's talk about how to find this. What is the width of each one of these rectangles? It's just 1. Okay? But what's the height of that first rectangle? What would we plug in to find the height of that first rectangle? Let me ask that. We plug in 0.5, right? Because we didn't use the left or the right, we use the number in between those two. Between 0 and 1, we'd have 0.5 there. So we've got f of 0.5. And then, what would the next rectangle, what would the height of that next rectangle be? F of 1.5. And then we're going to have 2.5 and 3.5. There. And let me pull up my calculator. Where's it at? Alright. There we go. So you can put it y equals if you want. I think this is just x squared, so I think I'll just type it in. We'll have 1 times 0.5 squared plus 1.5 squared plus 2.5 squared plus 3.5 squared. And for that, we will get 21. There. So that would be our estimate of the area under the graph. If we had a lot of time, we do left and right, and see that should fall in between those two right here. It's going to be a little bit better than doing our left or our right Riemann sum. Okay, questions? Very similar to what we were doing yesterday. We're just picking, rather than picking a left endpoint or a right endpoint, we're picking the numbers between our intervals right there. All right, let's continue. Okay, we are supposed to approximate the area bounded by the graph of f of x equals sine x between 0 and pi. Use the trapezoidal rule with 6 subintervals. Okay, now trapezoidal rule is, we're going to get to actually a rule that you can use shortcut sort of, but it just means we're going to use trapezoids this time. So once again, I'm going to cheat a little bit and use Desmos for this graph because it just makes such a pretty graph. Oh, that's Quiz Bowl attendance. That's not Desmos. Didn't do that yesterday either. All right. All right, and let's.
I watched you leave. I watched you just walk. Where were you? With you at the gas station. Oh yeah, I'm with you at the gas station. I got a piece of lunch.
All right. Oh gosh, why did I just do that? Okay. And let's go by over 6. No, not label. Step is what I need. Over 6. All right. Let's zoom out a little bit there. Okay. Okay. So just so I have a prettier graph that you guys can see better, let's put this over here. Sorry, I'm having some trouble rearranging here. I need to just go put these in the notes. I used to make students graph them more by hand. That's the wrong thing. Let's try this one. There we go. There we go. That's what we need. Okay. All right. So we're going to approximate the area bounded by the graph of f of x equals sine x between 0 and pi. Use the trapezoidal rule with 6 subintervals. So if we're going from 0 to pi, then we are going to, oh gosh, this didn't put this quite like I wanted it. Right here is pi over 3 and 2 pi over 3. We need halfway between that, which did not go on a grid line. Still probably better than my hand-drawn graph there. So this would be pi over 6. This would be 2 pi over 6, which reduces to pi over 3. This would be 3 pi over 6. Let's just write 2 pi over 6 right there. I've got 4 pi over 6. I got 5 pi over 6, and I got 6 pi over 6, right? I think it's a little easier to count up like that. All those values reduce for most of those, so of course 2 pi over 6 is pi over 3. 3 pi over 6 is pi over 2. 4 pi over 6 is 2 pi over 3. 6 pi over 6 is pi. So most of those are going to reduce. You can reduce them if you want, but if I'm letting you use the calculator, you can just type them in like that if you want also, right? If it's easier for you to think about that. So this one is going to give a much better estimation, but it is more difficult to do because we are not finding rectangles anymore. We are finding trapezoids. What is the area of a trapezoid? Okay, base 1 plus base 2 times height. Instead of doing divided by 2, I'm going to do a 1/2 out here, which would be the same as dividing by 2. Right? It'll just make our equation a little bit easier when we try to put some stuff together if we use that 1/2, but both are correct. You could do it either way. All right, so we're going to kind of spend a little time on this. We're going to do this a longer way. We're going to find the area of each trapezoid, right, which is always an option. Now, this first one actually, if I draw this in, this first one's not the easiest one to think about because is this first one a trapezoid? It's actually a triangle, right? Because the height of this base over here is 0. So I could just do area of a triangle here, or if I want to do this first one right here, I can just say, so I'm just going to call this trapezoid 1. That is going to be, I'm going to do 1/2. Now, in fact, let's just skip to trapezoid 2 and we'll come back to 1 because it's weird. Okay, here's our next trapezoid. This one is actually a trapezoid right here. What's a little bit weird about these trapezoids, what 2 sides of this trapezoid are going to be our bases? The left and the right, our vertical sides, right? So this side right here is B1, this is B2, right? Here's your height. It's kind of weird to call that the height because your vertical sides is what you think of as height. But the height is really sort of like the width here. So what would the width of that trapezoid be? It is pi over 6. So we got 1/2 times pi over 6, right? That is the width, which is also like the height of this trapezoid. And then we've got B1 plus B2, which I could actually figure out, or I could just do F of pi over 6. That would be the height of this left side, plus F of 2 pi over 6. And we'll grab our calculator here in a second. We're going to set this up first. Does that make sense? There, the pi over 6 is each one of these intervals right here has a width of pi over 6. We're going up by pi over 6. This is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. So all of our trapezoids are going to have a height of pi over 6. And then if we do the F of the left endpoint and F of the right endpoint, those are our base 1s and base 2s for this. Now let's go back to the first one. If I'm trying to use trapezoid formula, I would still have 1/2. I would still have pi over 6. What would be my bases here? Okay, I can do F of 0 or just 0 because 0, 0 is that point, right? This is going to end up being 0 right here, which is what makes it really end up just being a triangle instead of being a trapezoid. But it's going to work if you do it this way also. And then my right base would be F of pi over 6. Okay, so if we think about trapezoid number 3, Alright, here's this one. Okay, if we think about what's happening here, we're going to have 1/2. We'll have pi over 6. This time, the left base is f of 2 pi over 6, and the right base is f of 3 pi over 6. And then I've got trapezoid number 4. And that's 1/2 times pi over 6. And then I'll have f of the left base this time would be 3 pi over 6 and 4 pi over 6. All right, and you should sort of start to see a pattern here where we can just kind of use that pattern to find the rest of these. 1/2 times pi over 6, f of 4 pi over 6 plus f of 5 pi over 6. And then our last trapezoid would be 1/2 pi over 6, f of 5 pi over 6 plus f of 6 pi over 6. And you, of course, are welcome to reduce those and make that 6 pi over 6 pi for that. I just like, it just is easier to me to think of it like this, plus you're using the calculator, so it doesn't matter if you're typing in stupid fractions that you really should be reducing, right, for that. So, if I draw this in just so we can kind of see what we're looking at here. Now, I'd start to feel a little better when we start doing trapezoidal approximations, because we don't have much that we're missing on that, right? This is a lot better than our left or right Riemann sum. This is going to be a much more accurate estimation than what we had before. Now, let's talk about, because I don't really want to have to type every single one of these in separately. I would like to be able to type this into the calculator as quickly as possible. I definitely could just type them all in separately. But let's think about if we're trying to add all of these together, right? First of all, what do they all have? They all have a pi over 6, and they all have the 1/2. So I could factor that out. I could do 1/2 times pi over 6 if I want. I can make that pi over 12 right there. And then I'm adding all this other stuff together, so I would have f of 0 plus f of pi over 6 plus f of pi over 6 plus f of 2 pi over 6 plus f of 2 pi over 6 plus f of 3 pi over 6. Now, I'm going to dot this. My last one would be f of 5 pi over 6 plus f of 6 pi over 6. Okay. I could type it in as it is right now. It would be a little bit easier. But if I notice what I'm dealing with here, f of pi over 6 is listed 2 times, right? It's being added twice. Same thing here, right? Added twice. I skipped here, but 3 pi over 6, 4 pi over 6, and 5 pi over 6 are all going to show up twice because they're shared bases, right? They share the bases. The only 2 that are not shared are the 2 on the ends, right? So, the quickest way I could type this into the calculator would be to do pi over 12. I could do f of 0 plus 2 times f of pi over 6 plus 2 times f of 2 pi over 6 plus 2 times f of 3 pi over 6 plus 2 times f, parentheses, we're getting too many parentheses, getting carried away, 2f of 4 pi over 6, 2f of 5 pi over 6 and f of 6 pi over 6. Okay, so this still going to take me a little while to type in, but definitely a lot quicker than typing in each one of these separately. And now that we've kind of reasoned through it, we can kind of use this moving forward, right? So if I type this in, I'm going to have pi over 12. And then it is up to you, because this is a really simple function. It's just sine of x. You could put it in y1 if you want, or you can just do, which one do I like? I'm going to put it in y1. I'm going to do, you can just type in sine if you want. I don't like having to hit that green button to get sine, or you can do y1. Alright, so if we go back here to our home page, we could do y1 of pi over 6 plus 2 times y1 of, oh wait, I messed up. That's supposed to be 0, isn't it? 0 right there. Then y1 of pi over 6 plus 2 times y1 of 2 pi over 6 plus 2 times y1 of 3 pi over 6 plus 2 times y1 of 4 pi, still taking too long, it's annoying, isn't it, over 6 plus 2 times y1 of 5 pi over 6 plus the last one is just going to be 1 time y1 of pi for that. Oh, if we get an error, I'm going to cry. Okay, let's hit the green button before we hit enter there. And so we get 1.9541. Did you guys get the same? I hope that's right. Let's see. You guys get the same? Anybody else? Everybody else is like, I'm not doing that anyway. Seems too tedious. I'll just watch you take your word for it. It looks like I did it correctly, I think. Yeah, I think it did it right. Okay, so we're going to go 1.9541. Now, the good news is if we have equal intervals, we don't have to do all of that work that I did right there, because that took us way too long to do that one problem, right? Did I not write that down? Hold on, do I have a slide for that? Okay, oh, okay. It's on the next slide right here. So the trapezoidal rule, it has to have equal subintervals. It can be the change in x, which is that width that you're using. It was our pi over 6 divided by 2. Or if you want, you can do 1/2 times that change in width. That's what I did here. I did 1/2 times pi over 6. Or you could do pi over 6 divided by 2. Same thing. And then you just list f of the left endpoint once, all of the middle endpoint, all of the middle points are twice, and the last endpoint is just listed once. Okay. So if we have equal subintervals, we can just do that. We can just skip to that. Let's see if I got it do. We're going to skip 3 for the sake of time because they take a little while. Because 4 is a similar problem. So this one is a table problem. It says the table below shows the speed of a car in feet per second over 1 minute. Use a trapezoidal approximation with 6 subintervals to estimate the total distance that the car traveled over the minute shown. Because if we have a speed graph, right, we got miles, actually we got hour, no, we're doing feet per second here. So on our x-axis here, we would have feet per second. No, we wouldn't. Gosh, losing my mind. Sorry, guys. we would have seconds here, and then we would have feet per second here. So if I'm finding area, right, I'm multiplying the x times the y, feet per second times seconds. Seconds cancel. It just gives me the number of feet that the car traveled. So if I'm using a trapezoidal rule for this, what is the width, or we could call it the height, of each one of those trapezoids? It's 10. That is the distance. So this is your x-axis here. So you're looking at the interval that you're dealing with here. You're going up by 10. So that is your change in x right here. So you would say, I like to do 1/2 times 10, or you could do 10 divided by 2, like the formula says. Either one. They're the same, obviously. Then I'm going to do f of 0, 2f of 10, 2f of 20. Where do I find f of 0? What is it? It's just our y-coordinate that goes with this, right? So I would have this y-coordinate, 0 would be there one time. 15 would be there twice. 24 would be there twice. 31 would be there twice. 45 would be there twice. 52 would be there twice. 65 only once. Okay, all of those middle numbers get used twice. The end points only get used once. So if I do that here, I'm going to have 5 times 30 plus 48 plus 62 plus 90 plus 104 plus 65 there, and I should get 1,995. What would my units be for this? This feet. But now, you certainly can find the area of each trapezoid, draw it out, find the area of each trapezoid. We're going to see somewhere we're going to kind of have to do that. But on this one, it's a lot quicker to use that trapezoidal rule. Now, big key for that though, equal subintervals. If you do not have equal subintervals, you cannot do that, right? If you have intervals, like if this goes from 0 to 20 to 60 to 80, then you're going to have to do each trapezoid separately for that. But if it has equal subintervals, you can use this trapezoidal rule, which will save you a lot of time on these problems. All right, so let's look at this one. This graph gives us velocity in feet per second of a car traveling on a straight road from 0 to 50. That says shown above, but it should be below. A table of values for v of t at 5-second intervals is given. Approximate the area under the curve v of t on the interval from 0 to 50 with a Riemann sum using midpoints of 5 sub-intervals of equal length using the correct units. So we're using 5 rectangles, 5 sub-intervals from 0 to 50. Right? The graph is here. That helps me see. So my sub-intervals are going to be here at 10, 20, 30, 40, and 50. But I'm using a midpoint rule for this, which means I'm not using the point on either end. I'm using that point in between. So wherever that midpoint is in between is where I would draw my rectangle. So, if we think about each one of these rectangles, what is the width of each rectangle? Is 10, right? because we're going like from 0 to 10 here. So I would have 10 times, and then I need to do the height. What would I do for the height of that first rectangle? I will do, and they use a V here, so I'm going to say V of 5, right? And then I would have the next one. I would not use 10, I would not use 20, I use the number in between, so that would be V of 15. And then V of 25. And V of 35. And V of 45. And that'll be my 5 rectangles. And then those values we can get from the table, right? Because the table gives us those values. So we've got 10 times, we'll have 12 plus 15 is 30. V of 25 is 70. V of 35 is 81. And V of 45 is 60. Now, I do not mind you using a calculator for this, just for the sake of time, because these things can take a really long time. This would probably be calculator inactive. If it's on free response, what would you guys do there? Leave it. You don't have to simplify that, and you might mess it up, so I would leave it, unless you need the number to do something else with, later. Maybe you might need to compare this to something in part A. Then you would need to get the value. So whenever we do this, we get 2,530. What would the units be on this? It's not. So what you're thinking of feet per second would be like if we were dividing. If we were doing feet per second divided by seconds. That would be if we were finding the slope of this graph. We're not finding the slope of this graph. We're finding the area under this graph, right? So when we find area, we're doing, it's not feet squared, we're doing the x-axis. So like when I measure this first rectangle right here and I do that 10, that is 10 seconds, right? And when I do that first rectangle and it has a height of 12, that is 12 feet per second, right? When I'm multiplying, the value from the x-axis is seconds, the value from the y-axis is feet per second. So when I multiply that together, 10 times 12 will give me 120. That's the area of that first rectangle. The seconds is on top here, on bottom here. It just gives me feet. So this is just feet. So finding the area under the curve is like going, so everything we've done so far, we've started with a function. Like we had velocity, we found a derivative, it took us to acceleration, right? We were sort of like dividing. When we're finding area under the curve, it's taking us back up. It's taking us to position. We're looking at just distance for that. So it's 2,530 feet. Okay, questions? Okay, so we've got this graph. Actually, I think I've got a few here, right? Okay, you got 4 graphs right here. I want you to think about the left Riemann sum, the right Riemann sum, and the trapezoidal sum. You can sketch it in there if you need to. For all of these next ones, and think about whether you're going to have an overestimate or an underestimate for these particular graphs. Okay, so I'm going to give you a little time to do that. What do you guys think for a left Riemann sum? Is it going to be under or over? Under. Right Riemann sum then will be over. What about the trapezoid?
Under.
Okay, it is going to be under. For this, I like to make myself like bigger trapezoids to kind of think. Like this one right here actually would be a triangle. Right, and then this right here. It's a little hard to see because trapezoids are pretty good So it's a little hard to see, but you know, that'd be a little bit under right there. So it would be under for this one. For midpoint, you can't know. Well, I don't want to conclusively say you can't know. You can't know easily, and they're not going to ask you. Maybe there's a way to find out, but we're not going to be worried about midpoint. But for left, right, and trapezoidal, we do care about this. Now, we talked a little bit yesterday about left and right. If our graph is increasing, that Riemann sum is an underestimate, right? Okay, left, right, trapezoidal for this one. What do you guys think for the left? It's going to be over this time. Right Riemann sum would be under. Right? And like if you think about, you have your left corner has to be on the graph for that left Riemann sum. It's going to be over the estimate, right? All right, let's think about the trapezoid though. You know, trapezoid's a little hard to do on this one. Here is our, let's do like a, we draw in this trapezoid right here. Is that going to be over or under? Over a little bit, right? Here, that one's over. Okay? We are right here. Okay, 8. Left, over or under? Is under. Which means right is going to be over. Trapezoid. Over. On that one. Trapezoid's over on that one. You have to have the end points of your trapezoid have to be on the function. So you could, but it wouldn't be a correct trapezoidal sum.
Just draw like a little one.
Yeah. Like, I was just, especially for the trapezoid, I like picking a little bit bigger intervals, because when you're close to it, it just looks like it's on the line and it's kind of hard to tell. So, I mean, really for a trapezoid, you could make like a big interval here and do like this trapezoid and see a megazoid here, yeah. That, just to make it a little bit easier to see for that. Because the trapezoid is a better estimate, sometimes it's hard to tell with smaller trapezoids whether or not it's going to be above or below. It's seeming like it kind of to me here. That it's seeming like that might be the case. You may be thinking ahead to the conclusion that I want you to find. All right, what about left for number 9? It's under. Right would be over then. Trapezoidal, it would be under. Because if we draw in that trapezoidal sum, like maybe from here to here, well, that's not even, see, I don't even like trapezoid. Trapezoidal is too good. Let's do from, but if we did like one from here to here, you can kind of see that would be underneath a little bit, right? It's kind of hard when you get to over here. Like, yeah, I think that's under, but it's pretty close. You can't hardly tell for that. So, we said yesterday with left and right, concavity didn't matter, right? It was just increasing or decreasing that mattered. However, if we go back and consider our trapezoidal, let's look at what happened. Here we were increasing concave down, right? I'm going to write that down. Increasing concave down. And we had an underestimate. For 7, we were decreasing concave up, we had an overestimate. So at this point, it's a little hard to tell. Either concave up is the overestimate or it's the opposite of increasing, decreasing. We need more information, right? This graph is increasing concave up. So this was concave up. We had an overestimate. I'm flipping all over the place, I know. This one was increasing concave down. We had an underestimate. Does it seem like increasing or decreasing matters for trapezoidal? No, because we had increasing here and an underestimate, and we had increasing here, and we had an overestimate. So for trapezoidal, concavity is what's going to matter for this. Here, this one we have increasing concave down, and we get an underestimate, right? So you'll notice that the concavity is matching your over or underestimate, not the increasing, decreasing for trapezoidal. And a lot of times I just have to draw it. I just draw something concave up, and then I draw in my trapezoid because I've forgotten the rules for this. But if you kind of sketch it out, you'll be able to figure it out. So just to summarize what we talked about yesterday, a left Riemann sum is an overestimate whenever f is decreasing, right? Decreasing. All right, let me make sure. See, sometimes I've got to, left endpoint on the graph. That's an overestimate whenever the Riemann sum is decreasing. And then so an underestimate when f is increasing. Okay. A right Riemann sum is an overestimate. These are going to flip when f is increasing. And an underestimate when f is decreasing. And like I said, I always forget, and I just go over here and I draw myself a decreasing graph, and I say right endpoint, I need the right corner of my rectangle to be on that graph. Oh, look, that's underneath. Because that helps. Like when I see that, I feel confident. When I just try to memorize it, I get mixed up. Now, with a trapezoid, it doesn't matter about our increasing or decreasing. So we had concave up and concave down, right? So if we have a graph here, concave up, a graph here, concave down. I don't know why I didn't draw that one out. If we have a trapezoid and we're concave up, what are we going to get? Overestimate, right? So we're going to get an overestimate when f of x is concave up, and underestimate when f is concave down. Alright, so if we think of drawing this one in, draw pretty big trapezoids here. You got a little bit of a gap there. Okay, questions? All right. That is, yeah, did I do any with unequal intervals? Did I? No, I didn't have any on here. Let's hope the assignment didn't have any. Okay, so your assignment is going to be a worksheet.